Hi, and welcome back. So today we're going to talk about sections 10.5 and 10.6, which is solving equations involving trig functions. And our assistant Ariana is over here watching from the side, and so maybe if she has the same questions that you have, maybe she'll raise her hand and ask some of those questions for you. If not, send me an email with questions that you do run into, or stop by Zoom office hours. Okay, so in the last remote assignment, I gave you some warm-up problems to start kind of thinking about these types of equations. I have a few more warm-up topics that I want to talk about. So here is a preliminary idea. And the question that I'd like to ask is, how would you solve the following two equations? The first one is 2w plus 3 equals 4. And the second equation is 2w squared equals w. So I'd like for you to pause the video for a minute and think about how would you solve each of these two equations. Now, there's no trig functions involved here. This is strictly an algebra question. Okay, well, I'm going to talk about how, and again, if you didn't pause that video and think about how you would honestly solve these two equations. Okay, so when I look at these two equations, I notice that these two equations are different in terms of the types of equations that we have. In this first equation, we would say that this equation is linear in terms of our variable w, because w shows up in the equation, but it's not raised to any power other than the power of 1. And the second equation over here has a w squared as well as a w, and the highest power is a power of 2, and so we would say that this equation is quadratic in terms of that variable w. And because these are two different types of equations, a linear equation and a quadratic equation, my strategy for solving each of these two equations is going to be a little bit different. When I want to solve a linear equation, and I want to solve this equation for w, my strategy is to isolate the w. So in this particular example, when I have 2w plus 3 equals 4, I want to get the w by itself, so I've got to kind of peel away the extra pieces. So for example, I can subtract 3 from both sides, so I have 2w equals 1, and then I can divide both sides by 2, and we get that w is equal to 1/2. And that's how we would solve that equation. The strategy, again, for a linear equation is to isolate that unknown, that variable that we're looking for. On the other hand, this second equation, 2w squared equals w, is quadratic in terms of the variable we're trying to solve for. And whenever you have an equation where you have a variable that is higher than just a power of 1, maybe quadratic, meaning a degree 2, a power of 2 on the w, or even if you have higher powers, then your strategy with this type of equation, typically, there are special cases and special scenarios, but the general strategy is to move everything to one side and then try to factor. So our strategy is to move all terms to one side and then try to factor. So in this particular example, I have 2w squared equals w. So I'll subtract w from both sides, move the w over to the left side. So I have 2w squared minus w equals 0. So I have all the terms on one side, and now I ask myself, can I factor? And the answer here is yes, because I have a common w in both of these terms, so I can factor that w out. And I'm left with 2w minus 1. So I have w times 2w minus 1 equals 0. Now, once I have this guy factored, I have two things that are multiplied together, the w times the 2w minus 1, and those two terms multiplied together gives me 0, which means that either w equals 0 or the other factor, 2w minus 1, is equal to 0. So one of our solutions is w equals 0, and the other one I can solve for by adding 1 to both sides, and then dividing by 2. And so I have w equals a half. So in this second equation, our w is equal to either 0 or 1/2. Okay, so again, if you have a linear equation, you want to isolate the unknown. If you have a quadratic or a higher power, you want to move everything to one side and try to factor. Now, if you honestly paused the video and you solved both of these equations, or at least thought about how you would solve them, and on this second equation, you went about this in a slightly different method. Maybe one way that you thought to yourself was, you thought, okay, I have 2w squared equals w. And since there's a w on both sides, I'm going to divide both sides by w. And then that would give me, on the left side, that would leave me with 2w, and w over w is 1. So I have 2w equals 1. And then I divide both sides by 2, and I get w equals 1/2. Here's an issue, right? Because when we solved it doing the factoring method, we came up with 2 solutions. In this method, we only came up with 1, and here's why. There was one spot in here where we did a baddie. This right here is some illegal algebra. And so if you take a look right here, what I've done is I've divided by the variable. And so you probably talked about this in your college algebra class, but you might not have thought too carefully about it. But what you want to be careful of is you never, ever, ever, ever want to divide by a variable, because it's possible that that variable you divided by could be equal to 0. Now, if you know for sure that that variable is not equal to 0, you can go ahead and divide. But if that variable could be equal to 0, you do not want to divide by that variable. So this method of dividing to kind of cancel out one of the w's is not the way you want to go. Okay. All right. So again, we have our linear equation where we isolate the w. We have our quadratic equation where we move everything to one side and factor. Okay, so now that we've talked about the algebra of this thing, now we want to incorporate the trig functions. Okay, so now we are ready to talk about some equations that actually involve trig functions. And we're going to look at 2 examples today. And in both of these examples, our instructions are to solve each equation on the interval from 0 to 2 pi. And our first equation is 2 times the sine of x plus 3 equals 4. And our second equation is 2 cosine squared x equals cosine of x. And before we talk about some of the notation that's going on in this problem and these actual equations, I want to pause for a minute and tell you that what we have been doing for the last couple of class periods is work with trig identities. And trig identities are equations, like these are equations, but trig identities are equations that are true no matter what the input is into the trig function. So whatever theta or x you plug in makes the left side exactly equal to the right side. These are not identities. So these are, we're going to try this again. So these guys are equations, but they're only true for certain values of x, not for every single value of x. So when we try to solve each equation, what we're trying to do is we're trying to find an x value that makes the left side equal to 4. Or over here, we're trying to find an x value that makes 2 cosine squared of x equal to cosine of x. Okay? So again, equations, but these are not identities. Now, in terms of the instruction, solve each equation on the interval from 0 to 2 pi, this notation up here, this is interval notation, and this says, number one, that we're going to be solving for x, because in both of these cases, those are the variable we're looking for, and we are looking for values of x that are greater than or equal to 0 and strictly less than 2 pi. Now, what does that mean? What does that mean for us? Well, for us, what that means is that, number one, our value, our final answer, should be in terms of radians, because we're given 2 pi, which is not a degree measurement, that is a radian measurement. And the second is that our angle x will be only found by looking one time counterclockwise around the circle. So in other words, when we measure an angle, we're not going to get any negative measurement of the angles. We're not going to have any clockwise direction, strictly because we're told only to look between an angle of 0 and an angle of 2 pi. Okay, so all of those things come from the given information of the interval from 0 to 2 pi. Okay, so let's look at this first equation here. So in our first example, what I want to look at is I want to ask myself, what type of equation is this in terms of the trig function? So I see my trig function in here, and it's sine of x. And in terms of that sine of x, thinking of that as kind of a block, this is a linear equation in terms of sine of x. So like that first example that we did in our preliminary, because this is a linear equation in terms of sine of x, my strategy is going to be to isolate the sine of x term. Okay, so we can do that looking at 2 times sine of x plus 3 equals 4. To get sine of x by itself, I'll subtract 3 from both sides. So I'll have 2 times sine of x equals 1. And then I can divide both sides by 2. So I have sine of x is equal to 1/2. Okay, so I have now isolated the trig function. Okay, so we have sine of x equals 1/2. And so we want to find an angle x where x is between 0 and 2 pi. So one way to think about this, and of course there are many ways to do this, but this is how I like to think about solving this particular equation. So the first thing that I notice is that I have, and I'll just cross this guy out for now, and we'll work right here. So the thing that I notice is that when I have sine of x equals 1/2, this 1/2 is positive. Okay. And when I think about the sine function, I know that the sine function is positive in quadrant 1 and quadrant 2, because sine is y over r, and y is positive on the top half of the xy plane. So we're going to be looking for an angle here in quadrant 1 and an angle in quadrant 2. Now, I don't really know what those angles are going to be, but I'm just going to draw them in there anyway, and that's okay. Okay, so next, I want to think about what 1/2 is. So the sine function is opposite over hypotenuse, or y over r. So in terms of my two triangles, I can turn these angles into triangles, and the y value will be 1, and the r value will be 2 on both of these triangles. And so now I stare at these two triangles and I ask myself, do I recognize those numbers? And the answer is, yep, I sure do. Let's see. We've got our triangle with a 1 and a 2, and the third side is square root of 3. And so our reference angle on these triangles is 30 degrees. Okay, now in terms of radians, that's pi over 6. All right, so now that I have the reference angles, I now want to figure out what the actual angles should be. The first one is easy because the reference angle is my angle. And so our first angle is x equals pi over 6. Our other angle over here, well, that's 30 degrees short of 180. So if I look at that angle is 150 degrees. So we have x equals 150 degrees. And I can choose my favorite way to turn that into radians. One way is I can think of this as 5 times 30 degrees, so that's 5 times pi over 6, or 5 pi over 6. I can also break up my triangle into, or my circle into increments of pi over 6 and count them, and I'll end up with 5 pi over 6s. But in the end, our two angles that we have are an angle of x equals pi over 6 and x equals 5 pi over 6. So if we were to plug either pi over 6 or 5 pi over 6 into our original equation, we would have 2 times sine of pi over 6 plus 3, and that would be equal to 4. Or the same with 5 pi over 6. So those are our final answers. Now, one way it's sort of tough to maybe see if these are, if I have all of the solutions, or maybe I've missed some, or maybe the ones I have are inaccurate. So one way to kind of check your answer and sort of give a nod in the right direction is to pull out your graphing calculator and draw some pictures. So that's what we're going to do here. We're going to check our answer by looking at the graphing calculator. Okay, now what I have is I have a version of the graphing calculator on my computer. And so the very first thing that I'm going to do is I'm going to go to the mode, and I want to make sure that my calculator is in radian mode rather than degree mode. And then I'm going to go to y equals. Now our equation was 2 times the sine of x plus 3 equals 4. So the first function I'm going to plug in is 2 times the sine of x plus 3. So I'm plugging in one side of that equation up there, and now I'm going to plug in the other side, which is 4. All right, now when I hit graph, who knows what my window looks like? There's a picture. What we're seeing here is, here I've got the 2 times the sine of x plus 3, that's the wave, and then y equals 4 is the red line. Now we are only interested in x values between 0 and 2 pi, so I'm going to change my window to go from 0 to 2 pi, and I'm going to change my scale. I'm going to put a mark every value of pi over 2. And then I'm going to hit graph and see what happens. And so what I notice is that here is the graph of the left side of my equation, 2 times the sine of x plus 3. And then the red line is the y equals 4. And what I notice here is that those two graphs are equal at 2 points. And I can kind of double check that. So if I hit trace and I type in pi over 6, which is one of our answers, and I hit enter, when x equals pi over 6, that's the decimal approximation of pi over 6, our y value is 4, and that's one of the intersection points. And if I type in trace and type in 5 pi over 6 and hit enter, we get the other point of intersection. And from 0 to 2 pi, there are exactly 2 intersection points, which means we should have 2 solutions to our equation. All right. We're going to take a look at our second example. Okay, so now we are ready to take a look at the equation 2 cosine squared x equals cosine of x. And the first question that I want to ask myself when I want to solve one of these equations is I want to ask myself, what type of equation is this? And because we have trig functions in here, the question that I'm asking is, what type of equation is this in terms of the trig function? So here I see that our cosine function is squared, and then over here it's linear, but the biggest power is the square. So this equation is quadratic in terms of cosine of x. So my strategy, because I have a power higher than 1 on one of my trig functions, my strategy is to move all the terms to one side, have a 0 on the other side, and then ask the question, can I factor? So our strategy is to move all terms to one side, and then ask the question, can I factor? Okay, so in this case, we have 2 cosine squared x equals cosine of x. So I want to move everything to one side. So I'm going to subtract cosine of x from both sides. And so I have 2 cosine squared x minus cosine of x equals 0. Now, one thing you might be tempted to do in this first step is you might see, oh look, there's a cosine of x on both sides. I'm going to divide both sides by cosine of x. You don't want to do that because there is a possibility that cosine of x could be equal to 0. So you want to, at all possible, 99.9% of the time, you never want to divide by a variable. There are certain cases where you can do that safely, but for the most part, avoid dividing by a variable. Okay, so we now have 2 cosine squared x minus cosine x equals 0. And we ask the question, can I factor? And the answer is yes, I can, because I have a common term of cosine of x in both of these pieces. So I'm going to factor out cosine of x. And what I'm left with is 2 cosine x minus 1. So I have cosine of x times 2 cosine x minus 1 equals 0. All right, so now we're in a situation where we have one term times another term is equal to 0, which means at least one of these two expressions has to be equal to 0. So like we did with the algebra at the beginning, I can set the first term equal to 0 and the second piece equal to 0. So we have cosine of x is equal to 0, and we have 2 cosine of x minus 1 is equal to 0. All right, let's deal with this cosine of x equals 0 piece first. So when I look at this, that 0 on the right side, I know something about trig values. And one of the things that I know about trig values is that when you have cosine of an angle or sine of an angle and that value is equal to 0, the only time where sine and cosine is equal to 0 is when you're talking about one of the quadrantal angles. So this is a cosine value for a quadrantal angle, meaning one of those angles that shows up on one of the axes. So my strategy for trying to figure out what that angle should be is a little bit different than it is when I have things like cosine of x equals 1/2 or cosine of x equals root 2 over 2. When I see values like cosine of x equals 0, cosine of x equals 1, cosine of x equals -1, those are trig values that indicate to me that the angle is a quadrantal angle. So my strategy for figuring out what that angle should be is in terms of thinking about the unit circle. And remember, on the unit circle, the x-coordinate is the cosine value, the y-coordinate is the sine value. So the x-coordinate on the unit circle is cosine of theta. So I ask myself, along this unit circle, what points on this unit circle have an x-coordinate of 0? And the answer is this point up here on the top and the point down at the bottom. because this point up here at the top is the point 0, 1, the point at the bottom is 0, -1. So these are the two values, the two angles, where cosine of those angles are equal to 0. So this top angle, that's an angle of pi over 2, or 90 degrees. And the bottom angle, which I get to by traveling counterclockwise, is an angle of 3 pi over 2, or 270 degrees. So the values of x, where cosine of x is equal to 0, not the same x as the x-coordinate on the unit circle, but the value of our angle, cosine of this angle that will give us 0, are angles of pi over 2 and 3 pi over 2. Okay, so we've just found two solutions to our original equation. Okay. So we've solved this branch of the equation. Cosine of x equals 0. X either had to be pi over 2 or 3 pi over 2. Now let's look at the other half. The other half was 2 cosine of x minus 1 equals 0. So looking at this equation and kind of looking at it with new eyes, this portion of our equation is linear. And so my strategy here is to isolate that cosine of x function. So I can do that by adding 1 to both sides. So I have 2 cosine of x equals 1. Divide both sides by 2, and I have cosine of x is equal to 1/2. Okay, so now this 1/2 is one of those cosine values that goes along with one of our special angles. So my strategy here for figuring out what these angles are is to think first about the sine, S-I-G-N, of 1/2, and this value is positive, and cosine is positive in quadrant 1 for sure. Cosine is x over r, and x is positive on the right-hand side. So cosine is positive in quadrant 1 and quadrant 4. So we are going to be looking for angles. We're looking for one angle in quadrant 1 and one angle in quadrant 4. I don't know what those angles are, so I've just kind of drawn a random angle pointing in there. It's just to give me a picture. Okay, so now I'm going to create my reference triangles in both of these quadrants. And what I know is that cosine is adjacent over hypotenuse, or in terms of x's, y's, and r's, x over r. So the top number is our x value, and the bottom number, the 2, is our r value. So we have our hypotenuse on each triangle and that adjacent leg. And when I look at these triangles, if I'm thinking about a triangle that has its hypotenuse of 2, and that's not a very good picture of that. My hypotenuse is 2 and my adjacent side is 1, then I recognize this as my 30-60 right triangle because I have a 1, my hypotenuse is 2, my other side is square root of 3, and so my angle in here is an angle of 60 degrees, or I can think of that angle as pi over 3. Okay, so just by knowing 2 of the sides of these triangles, I recognize it as a special triangle, and that tells me that my reference angle is 60 degrees or pi over 3 radians. And the same is true down below. We have a reference angle of pi over 3. Okay, once I get the reference angle, then I ask myself, what is the actual angle that we're looking at? So on our first angle, that first angle is in quadrant 1, and so the reference angle is the angle that we're looking at. So our first angle is pi over 3, or 60 degrees. And our second angle, the one that is pointing down in quadrant 4, I want to get to that angle by traveling counterclockwise. My reference angle was 60 degrees, so that means that the angle we're looking at is 60 degrees short of a full circle of 360 degrees. So my second angle is 300 degrees, or if I want to think about that in terms of radians, which I do, in terms of radians, this is 5 pi over 3. How did I get that so quickly? Well, what my thought bubble on this was is that 300 is 5 blocks of 60, and so that's 5 times pi over 3 radians, and that's where I get my 5 pi over 3 from. I can also, if I want to, break up my entire circle into blocks of pi over 3 or blocks of 60, and I can count them, and I'll have 1, 2, 3, 4, 5 of them before I get to this terminal side. Okay, so we now have a total of 4 possible answers. We have x equals pi over 2, x equals 3 pi over 2, x equals pi over 3, and x equals 5 pi over 3, for a total of 4 possible answers. Okay. All right, before we stop the video, I want to go back over here and double check a picture for this guy. So what we expect is that we should have 4 intersection points. So we'll clear out our old graphs, and the left-hand side of our equation was 2 times, now it's cosine squared, so I can't use the cool kid notation of putting the square on the cosine in the calculator, so I'll use an extra set of parentheses. So I have 2 times cosine of x squared, and my other function will be just plain cosine of x. Double checking that my mode is in radians. Okay, and I want my window to go from, in our last example we already had 0 to 2 pi, so that's already good, and our x scale was pi over 2, and let's see what our graph looks like. Now this one's a little bit harder to see, and part of that reason is this graph is really kind of squished in here, and it looks like our graph doesn't go any higher than 2, so I'm going to change my window. I'm going to have my y minimum be maybe -2, and my y maximum, oh, it didn't like that I did that. -2, not -2, to a y maximum of +2, and let's see what happens when we graph. Now what I see is I see 1, 2, 3, 4 points of intersection. One is at pi over 2, here's one at 3 pi over 2, and my other 2 choices, one was pi over 3, so I can check for that by typing in pi over 3, and that's this intersection point right here. And our other value was 5 pi over 3, so I type in 5 pi over 3, and that gives me this point right here. So our total of 4 intersection points corresponds to the 4 solutions to our equation. Okay.